Good afternoon, class. This is section 2.1, Limits of Sequences, chapter 2, Limits. We're going to look at limits of sequences and then limits of functions at infinity, limits of functions at finite numbers, algebraic method. First, in 1.6, we looked at a sequence, which is a list of numbers, a sub 1, a sub 2, all the way to a sub n, which is the general term. We looked at the concept of a recursive sequence, also known as difference equation. The form is a sub n plus 1 equals f of a sub n. We also looked at the Fibonacci sequence, 1, 1, and then we start adding these two, we get 2, adding these two, we get 3, so on and so on. We also looked at arithmetic sequence when we add a constant recursively or explicitly. A sub n is a sub 1 plus n minus 1 times d, or a geometric sequence where we multiply by a constant ratio, we call it. A sub n plus 1 is r a sub n, and explicitly a sub n equals a sub 1 r to the power of n minus 1. Here's the summary of the section 2.1. First, a sequence is an ordered list of numbers, as it was mentioned. Then we look at the concept of a limit. Limit refers to the long-term behavior of a sequence. What happens to a sub n of a sequence in a long run? If the limit exists, the limit of a sub n as n approaches infinity. That's how we read that. We say it converges to L. If the limit is infinity or negative infinity or DNE does not exist, we say the sequence diverges. So to find the limit, simply plug in the value and observe. Let's look at some theorems. The limit of r to the power of n as n approaches infinity, what is the answer? It depends on the value of r. If r is between negative 1 and 1, not just 0 and 1, the answer is 0. If it's 1, the answer is 1. And if it's larger than 1, it tends infinity. Just to verify that with a simple example. If r is 1/3, 1/3 squared is 1/9, which is smaller than 1/3. 1/3 cubed is 1/27, that's even smaller. And that refers to the fact that when r is between negative 1 and 1, we end up with 0. On the other hand, if r is, let's say, 3, when you square it becomes larger, number 9. When you cube it, it becomes even larger, number 27, and refers to the fact that when r is larger than 1, the result is infinite. All right, so we're going to move on. The limit of 1/n to the power of p as n approaches infinity is 0 for p larger than 0. That is extremely important. When p is larger than 0, it remains at the bottom. Remember, when the exponent is negative, you move things around. In other words, a to the power of minus n is 1/a to the power of n, but 1/b to the power of minus m, it comes up. And that's why we use the exponent to be positive. All right. A geometric sequence, when we add them up, we have shown in algebra, it's a times 1 minus r to the power of n over 1 minus r. If r is between -1 and 1, this will go to 0 as n goes to infinity, and we get a over 1 minus r. This is the good old geometric sequence. B sub n is B sub 0 r to the power of n. In some texts, we may use a. That's why I'm going to put both of them. And this last part, when we add a constant, r represents the amount that remains. And normally, this refers to like medication and patience. R represents the percentage that is left in the body and sees the constant we add. And so the solution is slightly different. I have the proof at the end of the PowerPoints. You're not responsible for it. And I will discuss that further as we come across examples. All right. Let's start with a very simple example by calculating the first few terms. In this case, if you replace the n with 1, you get 1. 2, you get 1/2. 3, you get 1/3. 10, you get 1 over 10 or 0.1. It's getting smaller and smaller. And even that shows that this limit goes to 0. Therefore, it's convergent. And if we were to do a drawing, it looks like this. Note, for example, here is 2. Here's 1/2. In essence, you're looking at HA, horizontal asymptote. If you recall graphing rational expressions, the degree of the numerator is smaller than the degree of the denominator, and y equals 0 is the horizontal asymptote, which is the x-axis, in this case, the n-axis. Whereas here, if n is 1, you get -1 to the power of 1, which is -1. If it's 2, you get -1 squared, which is +1. If it's 3, again, you go back to -1, so on and so forth. And so it oscillates between -1 and 1, and it's divergent. If we were to graph it, we notice that it goes up and down. It oscillates between the two values. As it was mentioned, this limit, the limit of a sub n as n goes to infinity, if it exists and it's equal to L, you can pinpoint it with a number. Then we say the sequence is convergent and it converges to L. These are, in essence, limit laws. We will look at them later on, but the bottom line is, if a sub n and b sub n are two different sequences and each one has its own limit, the limit of the sum is the sum of the limits. The limit of the difference is difference of the limits. If you have a constant, the limit of a constant is constant, and if you multiply a sequence by that, you also multiply its limit by the limit of the product is the limit of the products. The limit of the quotient is the quotient of the limits. And of course, the denominator, as always, can't be 0. And if you're raising it to a power, the same thing works out. And I'm reminding you about what we just showed in the summary, that the limit of 1 over n to the power of p as n approaches infinity is 0, granted when p is positive. We write this limit, the limit of a sub n as n approaches infinity is infinity, if we can make a sub n arbitrarily large for all n sufficiently large, or this is equal to -infinity if we can make this sufficiently large, and this becomes arbitrarily negative. In both cases, the sequence diverges, these last two cases. Let's start with the warm-up example. I remind you about the theorem that was discussed in the summary. And not only R is between 0 and 1, even if it's between -1 and 1, is true. In the case of a sequences, normally we deal with positive values. Therefore, we write 0 to 1. So how do we deal with this? First and foremost, understand if we plug in, we get 2 to the power of infinity minus 1 over 6 to the power of infinity. And both of them are infinity. And infinity over infinity, we will discuss it later on. It's called indeterminate. That means we have to use algebraic techniques to figure them out. But for now, the technique is make up two fractions. This one is 1/3, so 1/3 to the power of n. This one you can think of it as 1 to the power of n, and therefore 1 over 6 to the power of n. And now, as we look at this theorem, it follows here. So each one, if I separate them into two limits, each one corresponds to 0. And that's the final answer. As I mentioned, we're going to plug in. So we start with the first one. The limit of 2 to the power of n as n approaches infinity. We're going to replace the n with infinity. And we get 2 to the power of infinity, which is infinity. Again, going back to the theory. In this case, we replace the n with infinity. And this becomes 0. The reason why is because this part is 1 over 2 to the power of infinity, which is 1 over infinity, which is 0. We are using negative exponential rule. 0 and 5, they add up to 5. Part C, the same thing. We're going to replace the n with infinity, and we know 1 over infinity is 0. Therefore, with 1, they add up to 1. All right. We want to find the limits of 2n squared plus 3n minus 1 over 5n squared minus n plus 8 as n approaches infinity. Anytime you're dealing with a rational expression and n or x approaches infinity, the technique is to divide by highest degree term in the denominator. In the denominator. I can't emphasize this enough. So we divide everything by n squared, the top and the bottom. So one way to write it, you can say times 1 over n squared. And when you divide everything by n squared, this is what you get. This becomes 2, this becomes 3 over n, this becomes minus 1 over n squared. The rest follows. And I hope you see that everything goes to 0 because n is infinity, right? Except 2 over 5, which is the final answer. The next one, again, n is approaching infinity. You divide by highest degree term in the denominator, which means n squared. So we divide everything by n squared. We get this one. So 3 over n minus 1 over n squared over 7 minus 3 over n. Everything goes to 0 with the exception of 7. And what I want you to notice here, this means 0 over 7. And because of that, equal to 0. Because if it's 0 over 0, then it's still indeterminate, okay? Or if it's 7 over 0, it blows up to either infinity or negative infinity. So 0 over any number other than 0 is 0. The next one. N is approaching infinity. We divide by highest degree term in the denominator, namely n. We are dividing everything by n. So the numerator is n, and the denominator is 2 minus 1 over n. Notice we are not losing the limit sign. You can't do that until the end. And that is extremely important. So right now, which I'm going to replace the n with infinity, I'm going to lose the limit sign. And please understand, this means infinity divided by 2. And infinity divided by 2 or divided by 10 or 10 billion makes no difference. It is still infinity. Infinity times a number 5, 10 is infinity. Divided by a number is infinity. If you square it, it is still infinity. We need to pay attention to that. What I want to quickly remind you about how we found horizontal asymptotes in pre-calculus, college algebra. Probably you've seen it a shortcut, but this is the justification as to how we find the limits. And this was something you learned before. If you have the function, let's call it r of x with a sub n x to the power of n, meaning the numerator has degree n over b sub m x to the power of n. And it doesn't matter what comes next, meaning the degree of the denominator is m, okay? If n is less than m, then your HA or horizontal asymptote was y equals 0. In other words, when you take a limit, you get 0. An example of that is E. This is the example of that. The degree of the numerator is 1. The degree of the denominator is 2. If n equals m, then your horizontal asymptote becomes a sub m over b sub m. And the example of that is part D. Okay. In part F, you may recall if n is equal to m plus 1 precisely, you have oblique asymptote which you find it by dividing and finding y equals mx plus b. But the bottom line is, in general, when n is larger than m, then the limit goes to infinity. There is no horizontal asymptote. Example of that would be part F. Again, this is a shorthand methodology to come up with the answer, but justification is what you see. We want to calculate the first 8 terms. So let's start with a sub 2 because a sub 1 is given. A sub 1 is 2. A sub n plus 1 is 1 minus 1/3 a sub n. If we replace the n with 1, we get a sub 2. So a sub 2 is 1 minus 1/3 a sub 1, according to this formula. Since a sub 1 is 2, If we replace a sub 1 with 2, we get 1 minus 1/3 times 2, which means 1 minus 2/3, which means 1/3. If I want to get a sub 3, according to this formula, is 1 minus 1/3 a sub 2. So a sub 2 is 1/3. 1/3 of that is 1 over 9. 1 minus that is 8 over 9 precisely. And it's fine and dandy, but you want 8 terms, so it takes a pretty long time to get to the next one and the next one and the next one. So I want to show you a quick, easy way using a graphing calculator. You can program this as follows. Whatever the value of a sub 1 is, in case you have to do 8 terms and it takes a long time, you want to cut down on time. Whatever the value of the first one is, you store it in X. This, using a graphing calculator, means store. Store. So that is stored in X. And you look at this one, because you're talking about the limit, a sub n plus 1 and a sub n and anything else, a sub n minus 1 for that matter, in the limit sense, they all become the same. If the limit exists, they go to infinity. So you can replace this with X, L, whatever. So in this case, the right side becomes 1 minus 1/3 X, 1 minus 1/3 X, and you store it in X. If you enter key repeatedly, it will give you those values. And the last one should help you see the limit. If this is not enough, you can always go with 1 or 2 or 3 more, and you should see the limit is about 0.75. And again, this is looking at it numerically, but I want to discuss this algebraically because that is actually the proof. And so the way it works is very simple. If the limit exists, then the limit of a sub n plus 1 or a sub n or any of them as n goes to infinity is the same, if it exists. So I can replace this one with L and this one with L, or X for that matter. So I'm going to replace this one with L and this one with L. Again, assuming the limit exists. And so if I move the negative 1/3, I get 4/3 L equals 1. If I multiply by 3/4, this is what I get. And I hope you know that 3/4 is 0.75. In other words, we used analytic method or algebraic method to prove this. Let's move on. All right, quickly reminding everybody of what we have seen, nothing brand new. Arithmetic sequence, we are adding a constant. Recursively, it's a sub n plus 1 is a sub n plus d. Explicitly is a sub n equals a sub 1 plus n minus 1 times d. For a geometric sequence, we multiply by a ratio. And with that being the case, a sub n plus 1 recursively becomes r a sub n. Explicitly becomes a sub 1 r to the power of n minus 1. And as I mentioned, this is the sum. And if r is between -1 and 1, this goes to 0. And we have s sub n equals a over 1 minus r. Just to remind you of the proof that you have seen in algebra, if you look at this line, which means because you're adding, it's a series in essence. And if you multiply this, we want S sub n. This is S sub n. Okay. If we multiply the, write this and then multiply it by R, let's see what happens. So this line is S sub n. Just write this. If I multiply this by R, okay, this one by R is this one, this one, this one, okay, so on and so forth, and this one. Why am I lining them up in this manner? Because I want to subtract the second from the first one. I'm subtracting the second from the first one. They cancel each other. Everything cancels out. We are left with A minus A or to the power of n. So S sub n minus R S sub n is equal to that. On the left side, we factor out S sub n. On the right side, we factor out the A. We divide by 1 minus R, and that's a proof for that. Now, if R happen to be between -1 and 1, or to the power of n goes to 0 as n goes to infinity, in other words, this goes to 0, and therefore A over 1 minus R is the answer. To make some sense out of this, let's look at a couple of examples. We want to add 1/2, 1/4, 1/8, and so forth, so it becomes a geometric sequence. Geometric sequence with the first term A being 1/2. What is R? If you divide 1/4 by 1/2, 1/8 by 1/4, 1/16 by 1/8, they become the same number, the same constant ratio, it's 1/2. So therefore, you're dealing with a geometric sequence. The first term A is 1/2, or happen to be 1/2 too. And so this formula, we're going to use this one, A over 1 minus R. One minus 1/2 is 1/2, and this is equal to 1, and we are done. So if you have 1/2 and add to half of that, which is 1/4, and then add to half of that, which is 1/8, and you keep on going indefinitely, you end up with number 1. Here's another example. We have a repeating decimal. We want to represent it as a rational number in fractional format. How do we do that? There is a method in algebra. You can look it up. We've done it in algebra before, like college algebra perhaps, or even intermediate algebra. But I want to look at it from the point of view of sequences, a geometric sequence. So 0.46 bar means 0.46, 46, 46. There are two ways of writing it. If you look at this part, is 0.46. This part zero point 0.0046. This part 0.000046. You can use decimals, you can use fractions, makes no difference. What is important to notice is the following. The first term is this or that in the form of a fraction or decimal. And I hope you see that it gets smaller by a factor of 100. That means R is 1 over 100. Now you could say This is 0.46. This is 0.01. It makes no difference. To find the sum, S sub n is A over 1 minus R, and we're going to look at it from both points of view, fractional format as well as decimal. From the fractional point of view, you're dealing with a complex fraction. We're going to multiply the top and the bottom by 100, in which case the top becomes 46, and the bottom becomes 100 minus 1, so 46 over 99. Or you could write 0.46 over 1 minus 0.01, which means 0.46 over 0.99, which is the same answer. Don't forget, every fraction must be put in its lowest term. This is done. This is a slightly different example where we have a mixed number and it's 5.75, 75, 75. And again, this part is 0.75 or 75 over 100. If you want to go with decimal, you can. If you want to go with fractions, you can. It makes no difference. If you go with fractions, the first term is 75 over 100 and R is 1 over 100. And we are simply going to add these three parts. Again, this you can go with 0.75 and the R you can go with 0.01. It's your choice, makes no difference. So 5.75 bar is 5 plus 0.75 bar, and 0.75 bar uses A over 1 minus R. Okay, so this part. It's a complex fraction. Let's multiply and divide by 100. And when we do that, again, remember the top becomes 75 and the bottom becomes 100 minus 1 or 99. And this fraction, 75 over 99, we can put it in its lowest term because there's a common factor of number 3. So we must. And as I mentioned, you can also use decimals as we did in the previous example. So 5 and 25 over 33, sometimes in some instances, they may want you to multiply 5 by 33 and add it to 25. So put it in a fractional format. Either way is fine. Just follow the instruction for full credit. The last thing I want to add in this page is that there are examples that are slightly different, and I have done them in my recordings of the practice exam. So what I want to show you, what happens if, let's say we have 2.14 bar. Understand this means 2.1444. And to do this, you can put 2.1 plus. The first one is 0.04. The next one is 0.004, so on and so forth. So work on the part that is the repeating decimal in this fashion in case you come across that. Recursion for medication. First, the geometric sequence and series that we are familiar with. B sub n is 3 times to the power of n. That's an example. We are using the basic geometric sequence in a recursive format. B sub n plus 1 is R B sub n. and the solution is b sub n equals b sub 0 r to the power of n. Please understand in some texts they use a, that's why I have both of them, which is absolutely the same equation depending upon what is the first term. So in this case, if I replace the n with 0, I get 1 times 3 is 3. If I replace it with 1, I get 6. With 2, 2 squared is 4 times 3, 12. And I have those numbers, which clearly indicates it's a geometric sequence of this format where r is 2. And you can see the r right here, or just 6 divided by 3, 12 divided by 6, so on and so forth. Clearly the first term, which we call it b sub 0 or a equals 3. Now we want to make a slight change. And we're going to modify it. How? Let's modify the geometric recursion by adding a constant term. This is like giving medication to patients. This difference equation arises from many real-world examples, such as when a patient is given some medication on a regular basis. So b sub n plus 1 is r times b sub n plus c. It's important to know what is r. R is the percent of the drug that remains in the body, what remains in the body. So the part, if they tell you it's this much has been absorbed, you have to subtract it from 1. C is the fixed amount, the constant. Remember the inflow we discussed in 1.6 that comes in at a specific time step. And so with that being the case, we end up with a slightly different formula. So this, I hope you see the difference between this one and this one. We are adding a constant, has a different solution, and I have the proof of that at the end of the PowerPoint. If anybody is interested in, you can look it up. So let's look at a simple case in general, and then we go to a patient situation. We want to solve this difference equation. B sub n plus 1 is 0.8, B sub n plus 4, B sub 0 is 5, and we want to find the limiting value. I want to tell you how we approach this, because mainly how do we get to the limiting value? There is a specific method. So when that is given, all you have to do is look at this one. Look at this one, compare and write the given. It is extremely important to be able to write the given. It really and truly makes life easy. So take a look. When we compare, the very first thing, B0 or A is 5. Now in a matter of comparison, R is 0.8, and the little constant is 4. Because we are dealing with word problem, I highly recommend you always write the given. Read the question a couple of times, write the given. The next one is to look at this equation. And replace b sub 0 with 5, lowercase c with 4, or with 0.8. So take a look. This one, and now we have it here. Now, everything else is some sort of algebraic technique to help us find the limit. So a quick recap. Compare this with this to find the given. Use this equation and replace the b sub 0 with 5, c with 4, and r over here, and over here with 0.8. Now, how do we simplify this? Let's look at the algebraic method. This is 0.2. I'm going to bring it out and cross this out and change this to 440 over 2, which is 20. Now, how do we combine this? If you can do it the way it is because you're distributing 20, by all means do that. If you don't see that, you can literally change this to x, which means now we have 5x plus 20 minus 20x. Or, as I mentioned, this is x, this is x. 5x, or 5 times 0.8 to the power of n, plus 20 times 1 is 20, plus 20 times minus 0.8 to the power of n, minus 20.8 to the power of n, or minus 20x. Now we can combine these two, 5x and minus 20x into minus 15x. So 20 minus 15x. All of which is done because we are interested in finding the limit, and it will help us take the limit. So we're going to take this limit. When we take the limit as n goes to infinity, this is 0.8 to the power of infinity. Because this number is between -1 and 1, this goes to 0. So 20 minus 15 times 0. This is 0. And the answer is 20. All right. Here's the next example. A patient is injected with a drug every 12 hours. This is the time step. Extremely important. Doesn't enter any of our calculations. Concentration will be reduced by 90% before each injection, and the new dose increases the concentration by 1.5 milligrams per milliliter. They want us to write the concentration after 3 dosage without going through the formulas. And so anytime you do word problem, I always want you to write the given. And by the way, since part B is using C sub n instead of a B sub n, we're going to use C sub n. So with that being the case, what do we write down? In the case of a patient, unless otherwise mentioned, B sub 0 equals A, which we are going to use C sub 0 equals A, it's always 0. Because initially there is no medication in the body of the patient. That's why it starts with the first, time step. By the way, every 12 hours, could be every 10 hours, every week, every day, every couple of days. So that is extremely important and has been calculated, doesn't enter anywhere here. So B sub 0 or A, we're going to call it C sub 0 or A, and that is 0. We need to find R and lowercase c. I hope you realize concentration is being reduced by 90%. What is left? 10%. So R is what is left. So 1 minus 0.9 or 10%. And what is the lowercase c, the constant? The dose increases by this much. Every time we add this much, it's the same constant. So that's the first thing, given. C sub 0, and why C sub 0? Because of the next part, or A is equal to 0. Lowercase c is the amount of constant. This is the amount that we add. And what is R? What is left in the body? 90% is gone, reduced by 90%. That means only 10% remains. And so first, we are interested in calculating this. The very first dose is 1.5, meaning 1.5 milligrams per milliliter. But what happens to the second one? Only 10% remains. So 10% of that, 0.15 remains. And then we add the constant 1.5. So 1.5 plus that is 1.65. So again, 10% of this is here and add 1.5. What happens to the next step? 10% of this previous step, that step 2, which is 0.165, and then the amount of constant 1.5 is being added. That's how you get this table. In part B, we want to write the expression for C sub n plus 1. First and foremost, we look at this formula. And we're going to change that to capital C n sub plus 1. And now, why did we write the given? Because it's going to make life easy here. Replace the R with what you have here, lowercase c with what you have here, and you're done. C sub n plus 1 is a 0.1 C sub n plus 1.5. Find the formula for C sub n. Look at this formula. We're going to use this formula now, and we're going to change the B to capital C. So we changed the B to capital C. And now, again, what's given? Use it here. C sub 0 or A, 0. R, here and here and here, 0.1. Lowercase c, 1.5. So the given that you wrote in the first step will really help out. And now we are going to use our algebraic techniques to do the job, just the way we did in the previous page. This is 0.9. I'm going to put it here. I'm going to cross it here. 1.5 over 0.9 is the same as 15 over 9 or 5/3. Now, what's interesting, if we choose n to be 1, 2, 3, we get this table. And you can try it. Replace the n with 1, 2, 3, and you see you get the same answer. Now, why are we simplifying it to this format? So the next part, which is asking for the limit. And now we can handle this easily because as n goes to infinity, 0.1 to the power of infinity goes to 0, and you have 5/3. And at this point, you really want to write the units. See, this was 1.5 milligrams per milliliters, so you write the limits. And again, 12 hours is important. Yes, it's a time step every 12 hours, but it doesn't enter any of our calculations here. Okay. Want to look at the last example. A doctor prescribes a 100 milligram antibiotic tablet to be taken every 8 hours. This is our time step, extremely important. Doesn't enter any of our calculations. Just before each tablet is taken, 20% of the drug present in the preceding time step remains in the body. How much drug is left after the third tablet? We want to make up a table. And before we do that, we notice in the next part says capital Q, which means anywhere we see B, we change it to capital Q, okay? So with that being the case, we want to write what's given. Can anybody tell me what's given as we look at this question before we start working on anything? What is given as we read this question? So a doctor prescribes a 100 milligram antibiotic to be taken every 8 hours. That means every 8 hours, fixed amount. That's lowercase c, fixed amount, 100 milligrams. Just before each tablet is taken, 20% of the drug present in the preceding time step remains. This is what we want, what remains. So it's R is 0.2. And dealing with patients, B0 equals A, in this case, Q sub 0 equals A is 0. This class, because we are dealing with patients, unless otherwise mentioned, this is always 0. The initial amount is always 0. It is the first one, Q sub 1, that we are adding whatever the constant is. So with that being the case, let's see what happens. The first one is 100. What happens to the second one? What remains? 20%. 20% of what? The previous one. So 20% of this is 20, and then we add a constant, becomes 120. What happens to the next step? 20% of this remains, which is 24. And then we add 100, becomes 124. Very straightforward. Part B, write the expression for Q sub n plus 1 in terms of Q sub n. So again, we are going to look at this formula first and change the B to Q. Or from the given is 0.2, lowercase c is 100. Find the formula for Q sub n as a function of n. We're going to use this formula. First, we change the B to Q. Change the B to Q. And now the given, let's plug in. Q sub 0 is 0, or here and here and here is 0.2. Lowercase c is 100. Replace them accordingly. Replace them accordingly. Now, this is always 0 because 0 times any number is 0. We simplify this to 0.8. We're going to put it out here under 100, cross it out, and this is the same as 1,000 over 8, which makes it 125. times the numerator, which is 1 minus 0.2 to the power of n. And of course, if you choose n to be 1, 2, 3, you can make up this table again. And you can try it on your own. The last part is to find the limit. So simply put, take the limit of q sub n as n goes to infinity. Again, this is r between -1 and 1. When we change it, when we raise it to infinity, goes to 0. So simply put 125. And anytime we answer, we really have to put the units if the units are given. So the limit of q sub n as n goes to infinity is 125 milligrams. What does it mean? If you give a 100 milligram antibiotic to this patient every 8 hours, it will never ever go beyond 125 milligrams, which has been calculated to be safe for the patient.